In Chapter 1, we solve a couple of simple ordinary differential equation systems just to get the feel for how to use PD2D before we go on in the next chapters to solve some actual partial differential equations. In particular, look at two examples. One is the spring problem, which you're probably already pretty familiar with. We have a spring that's attached to the roof, and y is the displacement from equilibrium of the mass, a mass m attached to the spring, and y equals 0 is the equilibrium point. If y is positive, that means it's pushed up above. Y is negative means below. And there are possibly three forces acting on this mass. One is the force of the spring, which is proportional to the displacement in the opposite direction. If the spring constant is k, then the force of the spring on this mass is minus ky. If y is positive, the force is negative. If y is down here, the force is positive, and it's proportional to the displacement from equilibrium. Then we're going to also assume that there's a frictional force that's proportional not to y, but to the derivative of y. It's in the opposite direction also. We'll call the constant b. So if the frictional force doesn't care what y is, it cares about y prime. If y prime is positive, if it's going up, the force is down. If it's going down, the force is up. And it's presumed to be proportional to the velocity. The bigger the velocity is, the stronger the frictional force is. That could be from the air or the spring itself. And then we're going to also possibly assume that there's an external force that's a function of t, which could be a magnetic force or wind or something external to the whole spring system. So by Newton's second law, the mass times the acceleration, the second derivative of position, is equal to the force. And there are three forces. There's one, the spring itself, which is proportional to the displacement in the opposite direction. There's the frictional force, which is proportional not to y, but to derivative of y with respect to time in the opposite direction of the derivative. And then there's the external force. So there's our equation, which you're probably pretty familiar with. Now, since PD2D only solves problems with first derivatives in time, we have to break this second order problem into two first order problems by defining v, the velocity, to be y prime, and then m times v prime, which is y double prime, is equal to minus ky minus b y prime, which is v, and we're assuming that there's no f. If there's an external force, there'd be a plus f of t here. So let's solve this problem using the PD2D GUI. M is 1, B is 2, K is going to be 101. There's no external forces. Initial conditions, y is 0, y prime is 10, which means it's at the equilibrium point, but it's moving up with a velocity of 10. Okay, so let's use the GUI to solve this problem. We're not going to do one of the prepared examples, so we'll leave that as 0. And it's a 0D problem. The dimension is the number of space variables, doesn't count time. And it's a time-dependent 0D problem. A steady state 0D problem would just be a system of linear or nonlinear equations. An eigenvalue 0D problem would just be a matrix eigenvalue problem. Neither one of those problems is particularly well suited for PD2D, but it will solve them, and it's not really the best program around for time-dependent 0D problem. That is a system of ordinary differential equations, but it will solve them. So let's do that. Number of partial differential equations. There's two equations. Are they linear? Yes. Okay, I'm going to define m to be the mass. Actually, I'm going to call it Rm Instead of m, that'll be the mass will be 1. K, which I'm going to call RK, will be 101. And B, with Fortran, real variables have to start with something other than I through N, so I don't want to use M or K, or they'll have to be integers. In this case, they are integers, so that'd be okay, but normally they wouldn't be. And B was, say, 2, so I've defined M, K, and B. And I want to go from t equals 0 out to, say, 5. This shows what the differential equations are. U1 is y, U2 is v. So it's just the for y prime equals something, well, C11 times y prime equals something, C22 times y v prime equals something. And we're going to call our variables y and v. Remember, it's a second order equation for y, but we broke it into a system of 2 first order equations for y and v, the velocity. And the exact solution of this problem is known. Y is equal to e to the minus t sine of 10t. So let's print out the error, which would be e to the minus t, use Fortran expressions, sine of 10 times t minus y. Okay, our first equation is just 1 times y prime equals v, and then m, which we've called rm, times v prime is equal to minus ky, which we called rk times y, minus b times v. Initial conditions, y of 0 is 0, v of 0 is 10. And we're done. Okay, well, all of that, the GUI or the interactive driver, this time we use the GUI because it's a simple enough problem, just creates a Fortran program which is all written for you, and a lot of defaults are chosen automatically for you. You can see, and you can make corrections here if we had made a mistake. Well, maybe we have, we'll see. There's the dimensions, definitions of M, K, and B. Time goes from 0 to 5 seconds. A lot of variables chosen for you, but what you chose in the GUI will be noted with a little comment that says input from the GUI. Okay, so here's the actual partial differential equations, and they're defined above so that you can, since C11 was 1, C12 is 0, F1 was V, because that's y prime equals V. Second one, C21 is 0, C22 is M, or Rm, times V prime is equal to, that was the minus Ky minus BV, and so forth. So typically you'll make some errors here, and then you can correct them in the Fortran. You don't have to go through the whole GUI session again. Okay, well, let's try running it and see if it works. It's a good chance it won't, but you run it using run PD2D. And it looks like it's working great. The error is 10 to the minus 9th or so. And let's look at the plots. Well, you can't see all of it here, but you can see that it's dying down. And anyway, the error is small, so this is off the page here. And here's well, the same plot that I just showed you, except that you can see all of it now. And the spring is vibrating up and down and gradually dying down because of the friction, the B term. And an interesting fact here is that the mass of that system, well, assuming there's no external forces, is the kinetic energy, which is 1/2 mv squared, plus the potential energy, which is 1/2 ky squared. Why is that? Because that's 1/2 ky times y. That's the energy that it takes to move it from 0 to y, because the average force, so the force is ky, but at the beginning y is 0, and at the end it's y. So on the average it's 1/2 ky, and that's the average force, and you've moved at a distance y. So that's the potential energy. Anyway, so there's the total energy is kinetic energy plus potential energy of the system, and if you take the derivative of that, you see you get 1/2 times m times 2y prime times the derivative of y prime, which is y double prime. 1/2 and the 2 cancels. Derivative of this is 2's cancel, and you get ky y prime. If you factor out a y prime, you have an m y double prime plus ky, which happens to be minus by prime, and so that gives you minus by prime squared, which is going to always be negative or 0 if b is 0. So if there's 0 frictional coefficient, then the energy is constant. If b is positive, it can't be negative. Frictional coefficient is positive, not non-zero, then the energy keeps going down, at least until y prime is 0. So that's kind of what we would expect. Okay, the other problem discussed in chapter 1 is the pendulum problem. And here we have a mass m that's connected to the origin by a rigid rod. This is not a string, it's a rigid rod, so you can't compress it or pull it out. And the mass is m, and the position of that mass that's connected by this pendulum to the origin is x of t, y of t, which we're going to try to solve for. And there are two forces acting on that mass. One is force of gravity, which is 0 in the horizontal direction and minus mg in the vertical direction. The other force is the force of the rod here, and it's going to always be in the direction toward the origin. Could be positive or negative, but it's going to be in the direction of the origin. And so there's the vector. This is the unit vector in the direction of the origin, minus x over L minus y over L, if L is the length of the pendulum here. So that's like the cosine minus sine. And so that's a unit vector. And what is the magnitude of the force? Well, that's going to be an unknown. We'll call it lambda of t. So there are basically three unknowns, x, y, and lambda. Lambda could be positive or negative. If it were a string, it could only be positive, but it's a rod, so it could be negative. So the mass times the acceleration, mass times x double prime, y double prime vector, has to be equal to this vector plus that vector by Newton's second law. So there are two second-order equations for the pendulum. The mass times the acceleration vector, which is x double prime, y double prime, is equal to the force of gravity, which is 0, minus mg, plus the force of the rod itself, which is in the direction of the unit vector minus x over L minus y over L, and has magnitude lambda. So there are actually three unknowns here, x, y, and lambda. But again, we have to break these into two first-order equations because PD2D can't handle second derivatives in time. It can handle second derivatives in space, but not in time. So again, just like with the spring problem, we'll define x prime to be u and y prime to be v, and those will be our first two equations. Then we have, this becomes m times u prime equals minus lambda x over L, and m times v prime equals minus lambda y over L minus mg. So there's four equations. But we also have to have that x squared plus y squared is always going to be equal to L squared. It always has to be a distance L from the origin. So we've actually got now 5 equations for 5 unknowns. What are the 5 unknowns? They're x, y, u, and v, which are the derivatives of x and y, and lambda. Now notice that this last equation doesn't have any time derivative in it. It's an algebraic equation. So this system is really a differential algebraic system, and that actually makes it harder for most programs, but not so hard for PD2D. But we'll just simply, we can say that's 0 times lambda prime there and go about our business. So there's our 5 equations, and again, let's use the GUI to solve example 2. So we're going to use the GUI to solve the pendulum problem with pendulum length 1, mass of 4, and g will be 32 feet per second squared. Use English units here. And we're going to start at x equals L, y equals 0, u and v, that is x prime and y prime, will be 0, which means we're going to start at a 90-degree angle, just as shown in that picture. And the initial lambda will be 0. Why? So we're going to start basically right here. X is L, y is 0. And we're just going to let go of the pendulum. We're not going to give it a push or anything. So the initial velocity is x prime equals 0, y prime equals 0. And lambda of 0 is also 0 because it's horizontal. It actually doesn't matter what lambda of 0 is because there's no differential equation on lambda, so I could put anything and it'll still work. But it should be 0. Okay, here we go. We're going to not use one of the prepared examples again. It's a 0D problem, time dependent again. This time there are 5 differential equations. It's still linear. Actually, it's not linear because you have a lambda times x and a lambda times y. And again, it says if you're not sure, assume it's nonlinear. Well, it actually is nonlinear, so. Okay, I'm going to define the g, the acceleration of gravity is 32. And m, again, I'll call it Rm, was, what did we say, 4? And L, which I need to call RL, well, I don't have to, but since it's an integer, but normally it won't be an integer. So it says names beginning with I through N must be integers, and I don't want L to be an integer, even though it is in this problem. So those are the only 3 parameters I think we'll need. Let's go from 0 to 5. And I don't want adaptive time step control. We'll discuss that later. You wouldn't know this, but I don't want it. There's a reason for it. We'll discuss later. You can always change it later. The discussion in the book explains why you don't want an adaptive time step. Normally you do, but for this particular problem, this differential algebraic system, you don't. Okay, so the unknowns are x y, u, which is x prime, v, which is y prime, and lambda, which I can't start with an L. Has to be A through H or O through Z, because the feature of Fortran, the unknown certainly cannot be integers. So I can't call it RL, so I'll just call it AL. I've already used RL for something else, so we'll have to call lambda AL. And no. Okay, here are the differential equations. The first one is x prime equals u. That's just the definition of u. The second one is y prime equals v. The third one is m, which we called rm, times u prime, that would be the second derivative of x, is equal to minus lambda, which we called AL, times x divided by L, which we called RL. Fortran, it's case insensitive, so it doesn't matter if it's upper or lower case. And then next equation is M times V prime, which is y double prime, is equal to minus lambda times y divided by L minus M times G. And the last equation is the algebraic equation, and that is 0 is equal to x squared plus y squared minus L squared. Remember, Fortran, the square or exponentiation, you have a double star instead of a caret. Okay, so I think those are our 5 equations. If I make a mistake, it'll be easy to correct later on. Initial conditions. Okay, x is L, y is 0. That's starting out at 90-degree angle there. The initial velocity is 0, 0. And lambda is 0 also, though I think it will work with any starting value there because there is no differential equation involving lambda prime. Okay, and we're done setting it up anyway. Now, it's not going to work, I can tell you that right now. Let's try it and I'll explain why it won't work. This is well, we'll see why. Let's try it anyway. Might have made some other errors, but one for sure. Well, if you look at the output, you'll see that it didn't work. Okay, now why didn't it work? Well, let's go back to the book. And the problem is basically that fifth equation that is the algebraic equation, x squared plus y squared minus L squared. That makes the problem very difficult. In fact, most ordinary differential equation solvers will have a terrible problem solving it. PD2D solves it just fine, but only if you simply use backwards Euler. So don't use Crank-Nicholson. There's no way you would know this, but it's explained to you in the book that so we have to go back, put Crank-Nicholson equal to false, and we don't want an adaptive time step. I already took care of that, so I think we just need to change Crank-Nicholson to false. And again, you just have to make the changes suggested in the book. They're very important. Normally for a system or ordinary differential equations, you don't have to worry about any of this, but that algebraic system, as I said, most equations, most solvers will not be able to solve it at all unless they're designed for differential algebraic systems. But so we're going to set adapt should already be equal to false, and Crank-Nicholson equals false, and take about 1,000 steps. And let's see what happens. So we'll have to do this with an editor. if we'd done the interactive driver, it would have asked us if you wanted crank Nicholson, and you could have said no there. Okay, I want to do 1,000 steps instead of 100 because that's suggested in the book. And there we go, crank Nicholson equals true. That's the default, but for this problem, it's just not a good idea, and you would have no way of knowing that except the book tells you. And I believe that's it because adapt is already set to false. Yeah, we already checked that. Okay, so let's try running it now. But this is typical that you have to make some changes. Most problems will never work the first time, and you don't want to go through the whole interactive driver session or GUI session again if you can avoid it, and usually you can avoid it unless you're making major changes like going from a 2D problem to 3D or time-dependent steady state or something. Okay, now let's see what happens. I think I know what's going to happen. Let's make this smaller. Unfortunately, you can't see the whole thing, but you can see enough to see that it's dying down. Now, that's not right because maybe in reality, physically, it probably would dampen, but we don't have any damping built into our equations. In other words, our system assumes no friction. The spring problem, we assumed a frictional coefficient of B here. There, we didn't put in any friction, so why is it dying down? Well, it's just, again, explained in the book that you just need to take more steps because the backward Euler method, which is the only one that works for this differential algebraic system, has this tendency to die down, so it's just a question of increasing the number of steps. Again, you wouldn't know that. It's all explained in the book, though. So let's increase the number of steps all the way to 100. Okay, so we get back into the editor and find the number of steps, which was defaulted. It was defaulted to 100, but we changed it already to 1,000 because we knew that wasn't going to be enough. And I'm going to change it all the way to 100,000. That seems like a lot of steps, but this is just an ordinary differential equation system. It won't take too long, hopefully. Okay, now let's run it. It's going to take about 100 times longer, but well, I'm going to pause it here. It's up to about 1 second. Okay, 4.7 seconds. We're almost done. So 100,000 steps. And it should look better this time. And you can see that it's not dying down now. This is X. Let's see. We want to look at Y. Well, let's look at it in the book. You can see it better anyway. Let's see. For example, 2. The book shows X. That was with only 1,000 steps, and it was dying down artificially. Then we changed it to 100,000, and it's not dying down. That's X. And I guess in the book it doesn't show Y or lambda, but the PD2D did create plots of X and Y and so forth, just didn't show them all. So everything seems to be working all right. Now physically what's happening here? So we started up here, and X goes from positive to 0 to negative. It'll go right up to here, and then it'll just go back and forth. And since there's no friction, in theory, it'll just keep going back and forth forever, from 90 degrees to 270 degrees over here and back, and x will go from -1 to 1, y will go from 0 to -1. Now in your homework problem, you're going to solve the same pendulum problem, but you're going to use a different initial conditions. You're going to give it a push. You're going to take the same pendulum system, and the initial conditions, y prime or v will be negative. In other words, you're going to start here, but you're going to give it a shove down. Well, what do you think is going to happen now? Well, it's going to go past the 270 degree point, and it may go all the way up to here and then start cycling, or it may not quite go up there. And the book tells you to try some different values of y prime to see what happens, and it'll all make sense physically. So your first homework problem is that same pendulum system, and basically change the v of 0, which is y prime of 0, to -7.5, and that will be hard enough to almost make it up to noon, 12 o'clock, but not quite. We're starting at 3 o'clock, and if you gave it a 0 initial velocity downward, it would go from 3 o'clock to 9 o'clock and back and forth. But if you give it a push down, it's going to go all the way past 9 o'clock up to almost noon. If you give it a little bigger push, it'll go past noon. And in fact, it says you can figure out exactly how big that v prime needs to be so that it will have enough energy to reach the top. And you do that by looking at the total energy, which is again the kinetic energy, 1/2 m times velocity squared, plus the potential energy, with y equals 0 being 0 potential energy. So the bigger y is, the more the potential energy, mgy. And if you take the derivative of E prime, you get exactly 0. So the total energy should be constant, and you're starting with y equals 0, so the 0 potential energy. If you calculate with the given y prime what the kinetic energy is, and if you get exactly up to 12 o'clock and just barely make it, then at that point the kinetic energy will be 0, and the potential energy will be mg times y equals 1. So you can figure out what the y prime of 0 has to be to make that balance. In fact, here in the book it shows what you should get for this problem with, if you give it a shove of -7.5, which is not quite enough to get it up to noon, 12 o'clock, and see what happens to x. It starts out at 1 at 3 o'clock, goes down to -1 at 9 o'clock. It's climbing up to noon, but it doesn't quite make it, and it falls back to 9 o'clock, x equals -1, and goes back to x equals 1 at 9 o'clock. Actually, it goes past that 9 o'clock. It goes up almost up to noon again, but not quite. Meanwhile, y starts out at 0. It goes down to -1, and it goes almost up to 1, but not quite. Goes back down to -1, almost up to noon on the other side, and so forth. So if you think about it, it's exactly what you'd expect. Okay, the other problem I've assigned is very different. This is also an ordinary differential equation, but the variable is x. It's a boundary value problem, not time. So you can't treat it as a 0D time-dependent problem like the spring and pendulum. You have to treat it as a 1D steady-state problem. The steady-state time-dependent refers to the time variable. The number of variables refers to space variables. So in the pendulum and spring problem, there were no space variables, and it was time-dependent. Here, there's no time, and there's one space variable. So it's a 1D steady-state problem, but you won't be able to use the GUI for this problem. You'll have to use the Galerkin method, which means you'll have to use the interactive driver, which asks a lot more questions, but you'll have to use it. You can't solve this with the GUI for a couple of reasons explained here. So this is a second order problem, but that's okay. It's second order in space, And it's a boundary value problem. At x equals -1, w is 0. At 2, it's 0. And d is discontinuous, goes from 10 to 1. And then we got this delta function here. So this is kind of a fancy problem. This is basically, it's like a string problem, but there's a constant force and then there's a delta force. So this seems like a fairly difficult problem. Next page is showing what the solution should look like. It's going to be 0 at -1 and 0 at 2. Those are the boundary conditions. And at 0, that d changes abruptly. And at x equals 1, there's this spike loading. Anyway, you'll have to use the interactive driver, and it will take care of that delta function automatically for you. You'll see it's going to be a little more difficult problem. As you know, the Galerkin method has a different format. It's basically of the form derivative of a with respect to x equals f, where a can be a function of w and w derivative. So a will be d of x times wx, and f will be this. And you'll have to write a couple of Fortran functions because the d is discontinuous, which means you're going to have to write a function d of x, which is, so the a will be d of x times w sub x, and you'll have to define a Fortran function d of x, which is 10 when x is less than 0 and 1 when x is greater than 0. It changes abruptly. The collocation method can't handle that. It can't handle the delta function either. So basically the Galerkin method can generally handle more difficult problems, but it's more difficult setup. And then the true solution to compare with, this is the true solution. You can basically just copy these functions as they are. You'll have to learn a little Fortran for this course, not a whole lot, but you know, most of the first two problems we saw, you really didn't need to write any Fortran except basic simple Fortran expressions. Here you have to do a little more because the d is discontinuous, and if you want to calculate the error, you have to know the true solution, and that's been calculated for you. And here it's, you know, to basically just copy this the way it is. Anyway, you'll have to read this carefully and you may need some help, but you'll have to use the interactive driver. You can't use the GUI. You'll have to use the Galerkin method. It's 1D steady-state problem, and use the Galerkin method. And when it asks you if you have a delta function, you're going to have to say yes. So it's going to take some work.